Alright, welcome back to another video by Firestarter Graphics and Engineering. Today I'm in my home studio, so you might hear cats, a water feature in the background. You might just hear a few things going on. Anyways, don't let that deter you from the information. Now, today we're going to be talking about how to find the coefficient of drag from what we call quadratic drag. So, you've probably seen my other video where we used Excel and numerical methods to solve for the coefficient of drag from either a coasting car or a rocket sensor data. So today we're going to take the sensor data from this level 3 rocket and find our coefficient of drag. It's almost like a virtual wind tunnel in a way, and I'll explain that more in just a little bit. So first things first, you'll notice on the left that my timestamps start at 13.9 seconds and move up. The reason why is because rockets don't have what we normally think of as free fall. Like they get to their peak and then free fall would be they fall back down to the earth. However, they have a parachute and a recovery device that opens up. So the only free fall chance they get is between motor burnout and what we call peak altitude or apogee. And that's when there's zero acceleration happening from the motor. It's just acceleration from Earth's gravity and the weight of the object. Okay, so with that in mind, we have our velocity in different units. We have our average velocity and our average acceleration, our mass, our gravity, and then this thing called beta. So what the heck is beta? Well, let's look into that. So, let's look at the derivation first. Okay, so this is how it's kind of derived. We know that force is equal to mass times acceleration, and differential equation of mass is a change of velocity over a change of time. Total force is equal to our negative drag force and our negative force of gravity. Substitute everything in right here, and then we look at this drag force, and we're going to say, okay, force of drag is equal to all of this. We should be familiar with this. But we're going to let this b value that we call beta equal all these variables and constants. We just want to simplify it. Then when we put it back into the drag force equation, we have what we call quadratic drag. Obviously because of this quadratic, this square. Now, let's put it back into the mass times acceleration. So we have this equation again. Remember, the force of gravity is nothing more than mass times gravity, or weight. Then we solve for beta, and we get this. Now, we start solving for that. That's why we had our average acceleration, our velocity, mass, and gravity, and that's what this beta value is that we have right here. All these beta values. Okay, so now what do? We have beta. That's great. Okay, so now we go back to where we let beta equal all of these, and then re-solve for the coefficient of drag. Now we have our beta value right here, which contains area and 1/2, and so we're going to and rho. So when we put this number here and then resolve, things will wash out and we get the coefficient of drag, which is right here. Now the beauty of this is this 0.67. I compared it to my results from OpenRocket, and what's really cool is OpenRocket got 0.63 in their component analysis using Reynolds number, surface friction, and a few other things. Now, granted, they don't have sensor data. OpenRocket has to do it a different way because it has no sensor data. So they calculated a different way. And there is a white paper you can read on that. There's a couple of them that I think are really good. The TR11 technical report by Estes Rockets about aerodynamic drag, and also the technical master thesis for OpenRocket, which is really good. Okay, so why do I say this is like a virtual wind tunnel? Because you'll see right here, as we approach 200 meters per second, okay, as we're getting really close to this value, we are converging our coefficient of drag to a certain value as well. Everything starts converging. It's the same thing as a wind tunnel. You start increasing that wind speed, you're going to start seeing how everything converges. Okay, so this number right here is actually our terminal velocity, which is this equation. Mass acceleration goes back to our quadratic drag again. let the change of acceleration be 0, and then solve for v, and that's going to be our terminal velocity, which is the square root of mass times gravity over our beta values, which is all right here. All of these values are terminal velocity. So it's kind of weird to say that at 13.9 seconds we have a terminal velocity, and then at 14 seconds we have a terminal velocity. So we're going to take an average of this and find out that it's 234 meters per second, which is right at the end of this graph, and that's where everything is starting to converge to. So that's why it's like a virtual wind tunnel, in my opinion. Anyways, I hope you guys enjoyed, and I hope it makes sense. And just keep engineering and have a lot of fun, and thank you for watching.